Welcome to another video in the video series of analog communication. In the previous video, we had discussed about various amplitude modulation schemes like DSB-FC, DSB-SC, SSB-SC and VSB-SC. Today we will discuss about the generation of DSB-SC, that is how the double sideband surface carrier signals are generated. DSB-SC can be generated by balanced modulators. Balanced modulators are of two types: single balanced modulator and double balanced modulator. And again, single balanced modulator can be used in two ways to generate DSB-SC. One is using linear circuits and the other one is using non-linear circuits. So let's get started. First we will discuss the generation process using linear device. The reason we are calling this single balanced modulator will be discussed in the later parts. First, let us discuss the process. This is the general block diagram of this method. MT is the message signal, which is given by AM sin omega MT, and CT is the carrier signal given by AC sin omega CT. MT is shifted by 180 degree and then put into this AM modulator, whereas here it is put into the AM modulator directly. So at this point the signal is minus of MT and here it is MT. In the AM modulator, the CT, that is the carrier signal, is also applied and the output is suppose x1t and here the output is x2t. Now they are added with an adder and the output is suppose yt, which is then passed through the bandpass filter and the output is DSB-SC. Generally in the transmitter end, where we modulate a signal, we have to use a bandpass filter because we want to pass the signals that consists of a carrier signal. So that's why bandpass filter is used. Whereas at the receiver end, where we demodulate the signal, we use a low pass filter because there we need to separate the carrier signal from the modulated signal. Now here you can see why in the adder we are subtracting x2t from x1t. That will be cleared in the later part. So let us proceed. Since MT and CT is passed through this AM modulator, the output x1t will be the modulated signal of MT and CT, that is the message signal and the carrier signal. So x1t will be AC into 1 plus k MT into sin omega CT, whereas x2t will be AC into 1 minus, because here the signal is minus MT, so 1 minus k into MT sin omega CT. Now these two signals are passed through this adder and they are subtracted. So yt is x1t minus x2t, and you will now understand why they are subtracted. So the result is AC sin omega CT plus AC into k into MT sin omega CT minus AC sin omega CT plus KAC MT sin omega CT. So this goes cancelled and we are left with 2 into AC K MT sin omega CT. I hope you understood why they are subtracted. If they were added, then this AC sin omega CT term will not get cancelled, and at the output, since we are passing this yt across the bandpass filter with a characteristic frequency of omega c and bandwidth of 2 FM, it will allow this signal as well, which is not desired because we desire to obtain a signal where the carrier signal is suppressed, and hence they are subtracted. And you can see the output consists of two sidebands with frequency omega c plus omega m and omega c minus omega m, and the carrier signal is not present here. So we have successfully generated a double sideband suppressed carrier. Now let us discuss generation of DSB-SC using nonlinear device in single balanced modulator. The general block diagram is like this. Here MT is the message signal, which is AM sin omega MT, and suppose CT is the carrier signal, AC cos omega CT. In this process we are using three adders. The carrier signal and the message signal in this adder are added, and in this adder the message signal is subtracted from the carrier signal. The respective outputs of these adders are passed through a nonlinear device, and then the outputs are subtracted again, where this output ZT is passed to the bandpass filter to get the DSB-SC signal. And here again the reason of adding and subtracting in these two adders and subtracting here as well is for getting the desired signal DSB-SC. I highly recommend you to use other combinations like adding the signals in both the adders and adding here as well, or subtracting here. So go ahead and do this and then comment below what you actually find. Then only you can better understand why they are done like this. Let us now proceed with this block diagram. So here x1t will be mt plus AC cos omega ct, and x2t will be minus mt plus AC cos omega ct. Let me mark this as 1 and 2. When these two signals are passed to the nonlinear device, the outputs will be y1t equals to a1mt plus AC cos omega ct plus a2 mt plus AC cos omega ct whole square. If you don't understand why I write this, you can check out the video on linear and nonlinear circuits, and you can definitely understand why this is written. And similarly y2t will be this. Now these two signals are subtracted to get the output ZT. So ZT is y1t minus y2t. So ZT will be a1x1t plus a2x1 square t minus a1x2t minus a2x2 square t. That is a1 into x1t minus x2t plus a2 into x1 square t minus x2 square t, which will be equals to a1 into x1t was mt plus AC cos omega ct minus x2t was minus mt plus AC cos omega ct, that is plus mt minus AC cos omega ct plus a2 into, this is a square minus b square, so a plus b into a minus b, that is x1t plus x2t into x1t minus x2t. So we are getting this. So eventually we are getting the spectrum of this output ZT is this. Now this ZT is passed through a bandpass filter of characteristic frequency omega c and bandwidth of 2 FM. That is, it will pass signals of frequency FC plus FM and FC minus FM. So the output, suppose ST, will permit only this signal and restrict this signal because it will allow frequencies of this region. So ST will be 4A2 into MT into AC cos omega CT, and by mathematical manipulation we are getting this. Suppose this whole term of 2A2 AC into AM be written as A dash, and with that we are having sine of omega C plus omega m into T minus sine of omega C minus omega m into T. And you can very well understand that in this signal ST there is no individual signal of message signal or carrier signal, and only the sidebands with frequency omega C plus omega m and omega C minus omega m is present. And this is the frequency spectrum of this DSB-SC signal. Now going back to the question, why this process is called balanced modulator, or rather single balanced modulator, and the answer is, in this setup the inputs are MT and CT, that is the message signal and the carrier signal, but at the output of this setup, that is the ZT, contains the message signal and a product signal of message signal and carrier signal. So at the output, MT along with this product signal is present, though the input had a message signal and a carrier signal. So this circuit is balanced about the carrier signal, and hence this balanced modulator is called a single balanced modulator, because only one component is balanced. So that is the end of this segment. In the next segment we will discuss about double balanced modulator, which is also called ring modulator. Thanks for watching. If the video was helpful for you, then please like and share it with your friends, and share your feedbacks in the comment box, and also share what you get after doing other combinations in this setup. Thank you. Do well.